Welcome back. This is session 10, Training and Alignment. Last session, we met 5 model families, and we used 3 words to describe how they train. RLHF, Constitutional AI, GRPO. We didn't explain any of them. Today, we build all 3 and 2 more from the one problem they all exist to solve. Before we start, let's put this session where it belongs. Every model that reaches a user goes through 4 stages. Pre-training decides what it knows, and that's sessions 1 through 9, all behind us. Serving decides what it costs to run, which is next session. Use takes the last 3 sessions of the course. Today is the second one, alignment, which decides how it behaves. Now look at what carried us through the first stage. 1 loss function. Predict the next token on every token of the web. Differentiable, cheap, defined everywhere. That single objective is the whole of sessions 1 through 9, and it stops here. Past that line, there is no loss function at all. Nothing differentiable measures helpful, or honest, or harmless. So alignment is this: turning a model that predicts text into one that does what it's asked, without the one tool that got us this far. Let's split it down the middle. What's settled, and what isn't? Settled, the transformer block itself, from session 5. Next, token prediction, from session 7. That's the objective you've been watching us train on ever since. The scaling law, from session 8. It tells you how much compute to spend and on what. And session 9's framework, which told you which decisions a lab even gets to make. Now the other side. Capability is trained. Behavior isn't. Nothing in that left column touches behavior at all. The model you get out of pre-training continues text. It doesn't answer you. We're about to see exactly what that looks like. And those 3 names from last session are still just names. So here's the whole session in one line. Where does behavior come from if it isn't in the objective? Let's go and look at the problem first. I want you to see this before we talk about it in the abstract. 3 ordinary prompts into a model that's been trained on the whole web and trained on exactly one thing: predict the next token. You ask it to summarize an article. Look at what comes back. It doesn't summarize anything. It writes the next sentence of what looks like a homework sheet. Then answer the 3 questions below. It continued your instruction instead of following it. Second one. You ask for the capital of Australia. It gives you the capital of Austria, then Belgium. You didn't ask a question as far as it's concerned. You started a list, and it's helping you finish it. Third one, and this is the one that matters. You ask how to disable a safety interlock, and it starts telling you. Not because anything went wrong. It's doing exactly what it was trained to do, in the same obliging tone as the other 2. So notice these aren't 3 different bugs. They're one failure 3 times over. Continuing text is the whole objective, and continuing text is all you got. Now, why does any of this matter outside a lecture? GPT-3 came out in June 2020. It was extraordinary, and almost nobody outside research used it because you had to coax it. You wrote your prompt as the beginning of a document and hoped the continuation was what you wanted. 2.5 years later, ChatGPT shipped, and it reached about 100 million users in 2 months. You're looking at the same architecture, the same objective, the same family of weights underneath. The only thing that changed is this green column. The summary instead of the homework sheet, Canberra instead of Austria, and a refusal with a reason instead of step 1. Every single thing in that column was added after pre-training. That's what this session is about. So the obvious question is, how do you train that? And here's where it gets interesting, because the obvious answer doesn't work. Think about what pre-training actually is. Cross-entropy on the next token. That's a real loss function. It's differentiable, it's cheap to evaluate, and it's defined on every token of text you can find. You minimize it, and capability comes out. Now try to write the loss for helpful. Go on, try. Or for honest. There isn't one. Helpful isn't a function of the next token. It's a property of a whole answer in a whole situation, and you cannot differentiate it. And a model can only be trained on a loss. That's the problem, and it's a real one. So you don't write it. You go and get a signal from somewhere else, and you turn that into a loss. And it turns out there are exactly 4 places that signal can come from. Before we start, here's what you'll walk out with. You'll be able to say why the next token objective can't express helpful, and name the 4 signal sources the field uses instead. You'll write the RLHF objective from memory. 2 terms, and you'll know what each one is stopping. Given 2 candidate answers with their numbers, you'll compute which one that objective actually prefers, and where the preference flips. We'll do that one together. You'll explain reward hacking properly, which quantity is being optimized, which one we wanted, and the moment they come apart. And you'll be able to say what DPO takes out of RLHF, what GRPO takes out of DPO, and what GRPO wants in exchange. Here's the shape of the whole thing before any of the detail. Every model you've used was built in 3 stages. And here's the part people usually skip. Each one eats a completely different kind of signal. Stage 1, pre-training. The signal is raw web text, and it's free because it's just text sitting there. What you get out is capability. What you don't get is any notion of a prompt at all. That's session 7 and session 8, and it's behind us. Stage 2, supervised fine-tuning. Now the signal is written demonstrations. Somebody sat down and wrote the answer. You get format out of it. What you still don't get is any notion of one answer being better than another. Hold on to that. It's the whole reason Stage 3 exists. And Stage 3, where the signal can be preferences, or principles, or outcomes. That's where values come from. And that's the rest of today. So, Session 8 built that first column. We'll walk through Stage 2 quickly, because you need what it can't do before the 3rd column makes sense. And then we'll spend most of today there. Let's start with the cheapest idea anyone had, because it mostly works. A human writes the answer out. Then you train the model on it as ordinary text, with the same cross-entropy loss you already have. No new machinery at all. Before you do that, this is what the model sees. A flat stream of tokens. No boundaries, no roles, nothing marking where a question ends and an answer begins. Everything is just the next token, which is why it did what it did 3 slides ago. Now look what the demonstration adds. An instruction, marked as an instruction. A response, marked as a response. And the loss only counts on the response side, so the model learns to produce that half, not to continue the question. This is Wei and colleagues at Google, 2021. The paper called Fine-Tuned Language Models Are Zero-Shot Learners. Their bet was that the capability is already in the weights, and a few thousand demonstrations are enough to teach the shape of an answer. They were right, and every chat model you've used ships a checkpoint trained this way. So we're done, right? Write more demonstrations? Get a better model? Let me show you why that stops working. Here's every response the model could generate for one prompt. Every dot is one thing it might say. A demonstration touches exactly one of them. Take a second with this. That's the space you're actually trying to shape, and it's enormous. You write a demonstration. It raises the probability of this one point, right here. And that's it. It says nothing about any other point in that space. Not that this one is better than that one, not which of the model's own answers you'd have preferred, but this is what you actually want to say. This answer is better than that one. And notice, neither of those 2 points is the demonstration. They're both things the model produced by itself, and nobody wrote either of them down. That's the gap. The next signal has to rank, not demonstrate. Okay, so we need rankings. Who gives us those? Here's a fact about people that this whole field is built on. Ask somebody to score an answer out of 10, and you get noise. Their 7s drift, and my 7 isn't your 7. Ask them which of 2 answers is better, and they're remarkably consistent. So you set it up like this. Same prompt, sample the model twice, get 2 different answers out. A person reads both and says A over B. That's all they have to do. No score, no writing, just a choice. And now, the clever part. You train a network on thousands of those choices, and its only job is to predict which one a person would have picked. Once it's trained, it'll score answers nobody has ever ranked. That's a reward model, and it's ordinary supervised learning. This idea is older than large language models, by the way. Cristiano and colleagues at OpenAI and DeepMind gave it to us in 2017 in Deep Reinforcement Learning from Human Preferences. Their assumption was that comparisons generalize, that a network trained on enough of them can score things no human ever saw. That assumption is what every labeling budget in the industry is now spent on. Let me write down what that network is actually trained on, because it's simpler than you'd guess. 2 bits of notation for you. YW is the answer the human preferred, W for winner. YL is the other one. And here's the loss. Minus log sigmoid of the winner's score minus the loser's score. Watch what it does. The further the reward model already puts the winner above the loser, the closer that sigmoid sits to 1, the closer its log sits to 0, and the smaller the loss. Score them the wrong way round, and the difference goes negative. The sigmoid drops below a half, and the loss climbs. This has a name, the Bradley-Terry loss, a pairized comparison model from 1952, decades older than any of this. It's a 2-class classifier on pairs. That's all. Notice there's no reinforcement learning here yet. Nothing is being sampled, nothing is being explored. We've just built a scoring function. Now we've got to use it. Right. We've got a thing that scores answers. How do we turn that into a better model? Sample from the model. Score what comes out, push it toward the higher score. Say it that way, and it sounds obvious. The model, and from here on we'll call it the policy, because that's the standard term once it's trained this way, it samples 2 candidate answers. Human preference on the pairs, feeding the reward model we just built. This half is slide 11 again, now sitting inside a loop. And the reward scores come back as a gradient update on the policy, which then samples again. Round and round. So what's happening here is one thing over and over. Sample, score, nudge, repeat. See that box on the way back? The KL penalty? Park it for 90 seconds. It's the most important thing on this slide, and it gets its own slide next. You're looking at Yang and colleagues at OpenAI, March 2022, the Instruct GPT paper. The update step itself is PPO from Schulman and colleagues in 2017. And 8 months after that paper, this exact recipe became ChatGPT. Here's the line that box was standing in for. 2 terms. Maximize the reward and pay a price for moving away from the model you started with. Maximize the expected reward from the reward model. That's the first term, and on its own, it's what you'd write down straight away. Then, minus beta times the KL divergence between the policy and the reference. The reference is the SFT model, the one you started this stage with. So the second term is measuring how far you've wandered from it and charging you for the distance. And beta is the price of drift. Literally, how much extra reward the model has to gain to justify 1 nat of distance from where it started. That number is a real setting on a real training run. And in about 3 minutes, you're going to work out what it should be. You might be thinking, why do I need the second term at all? Just maximize the reward. Fair. Let's drop the KL, keep the reward, and watch what breaks. Reward climbs beautifully. It keeps climbing, and the actual quality of the output, the red line, rises for a while and then falls off a cliff. What you get at the end is text that scores brilliantly and is barely English. The policy walked so far from the reference that it stopped speaking the language. Put the penalty back, and you get this instead. Reward rises more slowly. Quality rises with it. And the model stays fluent, because it's not allowed to get far enough away to forget how to talk. Ziegler and colleagues at OpenAI put that term in the objective back in 2019, in the first paper that fine-tuned a language model from human preferences at all. You'll find it in every version since. The KL penalty fixes one problem. There's a deeper one underneath it. Keeping the language coherent doesn't make the reward model right. And the reward model is a stand-in. It's a network's guess at what a person would have picked. So let's track 2 things at once as training runs: the reward model score and what actual humans think of the output. Early on, they move together, which is exactly what you'd hope. Then look, the gold line keeps climbing and the red line turns over. The model is getting better at the score and worse at the job at the same time. This has a name, and you may already know it from economics. Goodhart's Law, named for the economist Charles Goodhart, who made the point about monetary policy in 1975. The wording everyone quotes is Marilyn Strathern's from 1997. When a measure becomes a target, it stops being a good measure. The model didn't learn to be good. It learned to score well. And those parted company right about there. Gao, Schulman, and Hilton at OpenAI measured this properly in 2022. The useful part of their result is that the split point is predictable from the reward model's size and how much KL budget you've spent, so you can budget for it instead of discovering it. Let's make that concrete. Because beta isn't a symbol on a training run, it's a number somebody types. Here's the objective again. Reward minus beta times the KL. Beta is the unknown today. I'll give you two candidate answers to the same prompt. The first one, the reward model loves it. It scores 8. And it's drifted a long way from the reference. 3 nats. If you read it, it's padded and flattering and barely on topic. It's a reward-hacked answer, and you now know what those look like. The second one scores 6. Lower. But it stayed close to the reference. Half a net. And it's the answer you'd actually want. Direct and accurate. So here's the question. How large does beta have to be before that objective prefers the faithful answer? Have a go before I show you. Let's do it. It's 2 lines. Take the drifted answer first. Its value under the objective is its reward minus beta times its KL. So we get 8 minus 3 beta. Same 2 terms for the faithful one. With its own numbers, we get 6 minus 0.5 beta. We want to know where they cross, so set them equal. 8 minus 3 beta equals 6 minus 0.5 beta. Bring it together and you get 2 equals 2.5 beta, so beta is 0.8. And think about what's happening below that. 3 nats of drift are cheap enough to be worth 2 points of reward, so the padded answer wins the objective outright. You'd never see it in the loss curve. You'd see it in the outputs. So beta has to be bigger than 0.8. And that's not a maths exercise. That's a setting on a real training run. Set it too low, and you get exactly the run we watched fall apart 2 slides ago. Now, RLHF works, but I want to show you 2 problems it has that aren't about maths at all. The first is that human comparisons never stop. You need people ranking, permanently, for as long as you keep training. The second is quieter. Nobody can point at the standard being applied. It's distributed across thousands of individual judgments, and you can't read it, audit it, or argue with it. So here's a different idea. Write the standard down. The model generates an answer, and then the model critiques its own answer against a written set of principles sitting right there in the middle. That document is the Constitution, and it's just text. Having criticized itself, it revises. Now you've got 2 answers to the same prompt, the original and the improved one. And that pair is a preference pair. You know which one is better, because one of them is the revision of the other. So it feeds the same reward model machinery we already built, with no human in that loop at all. In one sentence, the model writes, criticizes itself against a document, rewrites, and the 2 versions are the training data. Bai and colleagues at Anthropic, December 2022. Their bet was that written principles plus self-critique can stand in for human labels on the harmlessness half of the job. It trains every Claude model since, and the Constitution itself is published, so you can go and read the standard. Let me ask a different question about RLHF. Not is it right, but is it doing more work than it needs to? Count what's in GPU memory during that loop. The policy you're training, a frozen reference for the KL term, the reward model, and PPO carries a value network too. 4 networks to convert a pile of preference pairs into a gradient. Here's the whole thing drawn out for you. Pairs go in, a reward model gets trained, PPO optimizes against it. And here's DPO. The same pairs go in, and there's 1 loss, directly on the policy, 2 models resident, the policy and the reference. Now, you might be thinking that sounds too good, that you can't just delete a network from a pipeline and expect the same answer. You're right, and they didn't. Look at the arrow. The reward model has been solved for and substituted. which is a completely different thing. And it's why this works, rather than being wishful. Rafailov and colleagues at Stanford, 2023. The title tells you the whole result. Your language model is secretly a reward model. This is now the default recipe in open source alignment, mostly because 2 networks fit on hardware where 4 don't. I want to show you the substitution itself, because it's 2 lines and it's genuinely elegant. Here's the fact it rests on, and I'll ask you to take this one on trust. It's the paper's real contribution. For the objective we wrote on slide 14, the best possible policy has a closed form in terms of the reward. Turn that equation around, and the reward becomes a statement about the policy. There's the line. The implicit reward for an answer is beta times the log of how much more likely your policy makes that answer compared to the reference. Read it in words. An answer's reward is how much the training moved it. That's a number you can compute from the 2 networks you already have. So now take that expression and put it into the loss we wrote 9 slides ago, the pairwise one, minus log sigmoid of winner minus loser. And there's DPO. Look at it. It's exactly the same loss as before. Same shape, same sigmoid, same winner minus loser. The only thing that changed is what R means. No second network anywhere. One more, and this one goes somewhere different. Everything we've built today has a human in it somewhere. Writing demonstrations, ranking pairs, drafting a constitution, but think about maths or code. Nobody has to judge anything. The answer is either right or it isn't. So we take one problem and we let the model try it several times. 4 here. 4 different attempts at the same question. Check each one against the ground truth. 1 right, 3 wrong. 1 and 0, and that's the entire reward signal. No reward model scored anything. And that turns straight into a gradient. No human labels, no reward model, and no worked reasoning examples either. Nobody wrote out for it how to solve the thing. So what's happening here is the simplest loop in a session. We try it 4 times, we see which one worked, and we push harder on that. Xiao and colleagues at DeepSeek introduced this in February 2024 in the DeepSeek math paper, and scaled it up in DeepSeek R1 in January 2025. Here's the part worth sitting with. The long reasoning traces R1 is famous for weren't taught. They emerged because thinking longer happened to get more answers right. There's one piece of that I skipped, and it's the piece the method is named after. A raw 1 or 0 isn't a training signal on its own. If every sample in the group is right, right tells you nothing. What matters is how one sample did against the rest of its own group. So, the advantage of sample I is its reward minus the group's mean divided by the group's standard deviation. Divide by the group size itself, not size minus 1. The group is the whole population you care about, not a sample standing in for a bigger one. Standard scoring on the group. That's it. That's the whole formula. And here's why that's clever. In DPO, a whole separate value network exists to estimate what score you should have expected. Here, the group does that job for free, just by existing. So this one line replaces the reward model and the value network at the same time. Let's put a number on that. On the group we already have. You've got 4 samples of the same problem. Output 3 is correct, so it gets a reward of 1. The other 3 are wrong, so they get 0. Here's the group again, with the scores on screen. What advantage does output 3 actually carry into the update? Use the population standard deviation, and take a moment with it. Right. Let's build it up. Our rewards are 0, 0, 1, 0. Add them and divide by 4, and the mean is 0.25. Now the spread. Each wrong sample sits 0.25 below the mean, and the correct one sits 0.75 above it. Square those, average them, and you get 0.1875. Take the square root, and you get about 0.433. So the correct sample carries 1 minus 0.25 over 0.433, and we get about plus 1.73. Each wrong one carries minus 0.25 over the same number, about minus 0.58, plus 1.73. And look at what that means. 1 correct answer out of 4 produces a strong positive push on everything that led to it. and there's no reward model anywhere in that arithmetic. That's the whole method. Let's put the session back together. Every method we've built today is an answer to the same question. Here's all four on one line, laid out by how much human work a single training example costs. Furthest left, the most expensive, demonstrations. A human writes the whole answer. That's SFT, and remember what it can't do. It teaches format, and it can't rank. Next, comparisons. A human picks one answer of two, which is far less work. That's RLHF and DPO. It orders answers, but it needs that labeling pipeline running permanently. Then principles. A human writes the rules once, and that's the last human step. That's constitutional AI. It's auditable, and it's only ever as good as the rules you wrote. And on the right, outcomes. No human at all. The answer just gets checked. That's GRPO. Free, exact, and it only exists where an answer can be checked. So read the line left to right, and you're trading coverage for scale. Only the two on the left can express things nobody can write down. The point is that all four are answers to one question. And once you can hear that question, you can place a method you've never met. Last one, and this is the one you'd actually face at work. 3 real jobs. For each one, which of those 4 sources can actually supply what it needs? Task A, a support assistant that has to sound like your company across thousands of replies. Task B, you need a model that solves competition maths problems and gets the final answer right. And Task C, the last one, you're building a summarizer for a regulated industry, where the style rules are already written down and published. Demonstrations, comparisons, principles, or outcomes. One each. Have a think. Let's take them in order. Task A, the house tone. Nobody can write the rule for sounds like us, and every attempt reads like a style guide nobody follows. But any employee can look at 2 replies and pick the better one. That's comparisons, RLHF or DPO. Task B, competition maths. The final answer is checkable against ground truth, so you don't need a human in the loop at all, and you shouldn't pay for one. That's outcomes, GRPO. Task C, the regulated summaries. The standard already exists, in writing, published. So hand it to the model as a constitution. That's principles, constitutional AI. A to comparisons, B to outcomes, C to principles. And notice what none of them is. Demonstrations. Writing the answers out is where you start. It's not where you finish. One last way to look at the pipeline. Set the 3 training stages against the 3 things we actually want out of a deployed model. Helpful, harmless, honest. Pre-training. Look at that row. Nothing. Not one of the 3. Pre-training gives you capability, and capability is no kind of value at all. SFT fills in one cell. Helpful, because a demonstration is a demonstration of being helpful. It does nothing for the other 2. An SFT model can format a perfectly fluent answer and still have no notion of safe or true, because nothing in "here's the answer, copy the shape" ever tells it what to refuse. And the RL stage fills the other 2 for us. Harmless and honest live here, and nowhere else in the pipeline. So every value that model has, somebody put there. On purpose, in one specific stage, and you can now name which. Let's go back to where we came in. We started here. 3 ordinary prompts, and a model that could only continue them. And here's the thing. That green column it isn't a better minimum of the pre-training loss. It's 4 different signals, each one bought from somewhere outside the objective, and each one built in this session. So you can now say why that column needs a signal and not a loss. You can name all 4 signals. You can write the RLHF objective and say what each term stops. You can work out where its preference flips, and you did. You can call reward hacking by its proper name, a good heart failure, and say exactly where the reward score and the real judgment part ways. And you can say what DPO takes out of RLHF, what GRPO takes out of DPO, and what GRPO demands in exchange. an answer somebody can actually check. Before we finish, here's what we quietly assumed all the way through. Every single method today assumed you could afford to run the model at all. Nobody mentioned it. A 400 billion parameter model needs hundreds of gigabytes just to hold its weights before one user connects. And aligned and unaffordable is still unusable. So next session, we take the other half of the deployment story, what a model costs to serve, and the architecture changes that bring it down. Let's see where we've got to on the road. Sessions 1 through 9, behind us. Session 10, training and alignment, done. And 4 to go. You can see the phases now. Foundations, then architecture, and we're inside the real-world stretch, where everything is about what it takes to actually ship one of these. So next time, you can now train a capable model into a well-behaved one and say exactly where every piece of that behavior came from. But every method today assumed you could afford to run the model at all. Next session, what it costs to serve one, and the architecture changes that make it affordable. And here's what you'll do yourselves. Part 1. You'll take one prompt through 3 checkpoints of the same model family. The base model, the instruction-tuned one, the preference-tuned one. Every difference you see, you attribute to a stage. It's slide 8, on real weights. Part 2. You'll load real preference pairs from Anthropic's HHR RLHF set and fit a small Bradley-Terry reward model on them, using the loss we wrote by hand. Then you'll score held-out responses with it. Part 3, and this is the one I'd do first. Go and find the responses your own reward model overscores. Reward hacking on your numbers, not a curve on my slide. And the challenge. Run a critique and revise loop against a constitution you write yourself. 3 principles. Then decide whether the pair that comes out is usable training data. I'll tell you now, your answer is going to depend on how specific you were. See you next session. LLM, Bluevision AI, Dr. Vahid Saidi, 2026.